So supervised learning, right? The supervised learning, we have a regression and we have a classification. In the previous workshop, I already talked about what's the regression and the classification. The difference is only about the output variable. The regression, the output variable is a continuous variable. For the classification, the output variable is a category variable. So today, before I go into the regression, where the target variable is continuous, I want to talk about the general solution for the supervised learning. Actually, that is called maximum likelihood estimation, but it's a little bit not precise. Actually, it's not general solution for supervised learning. It's a general solution for function-based models. What do I mean by function-based model? Assume in linear regression you have kind of function like w y equal to wx plus b. This is function form, right? And you may have this is a linear regression function. You may have another function, maybe y equal to x squared plus x plus x root square. Like this. This is also functional form, but here I already gave the parameters. Let me remove the parameters. Make the parameters unknown. Maybe it's become A, and here it's become B. Yep, now here we have a parameter A and B. So maximum likelihood isn't maximum likelihood fitting a probability spread to observation. I'm not sure what you mean the spreads. What do you mean, Baron? Probability spread? Fit the probability spread is generally the maximum likelihood estimation is to let you describe the most probable parameters using the hypothesized probability distribution. I will dive into it later. If you still have questions after I give you the whole picture, please ask me. So fitting the parameters of the finding the parameter of that best fit the observed data. Finding the parameters of the probability distribution. Actually, we want to find the parameters of these functions. Then we use the probability distribution as a tool. Let me go back to this later. So now we have WB for linear regression. We have AB for a quadratic function. If neural network, we have more nested functions. We have a WB in the first layer, WB in the second layer. So that's that's the thing. Actually, in one layer, we have different WB because in neural network, we have different neurons. But that's another story in the last week, week 10. So now how we can find the A and B? I give you a data set. I give you for maybe the height and weight of people. So I want you to train a model using height to predict weight. So now you know X, you know what's the Y, what's X. You have a lot of Y and X. So how you can find the optimal W and B, which fit to this X and Y, the weight and height and weight data. So let me just formalize this problem, okay? We have parameters. I call parameters theta. Yeah, I think I need to make it a little bit bigger. Theta. In linear regression, we have, let me make it a little bit concrete. We have WX plus B. I don't want to use X here and B here. Actually, it's just a variable. It can be any notation. I just follow my my habits. I always use beta 1 for X and beta 0 for B. Okay, so now in linear regression, this parameter become beta 0 and beta 1. If you want to generalize to the previous workshop, the parameter in the k-means could be centroids, right? It can be if you have two centroids, you define the number of clusters equal to 2. So the parameter would be centroid 1, the centroid 2. The centroid is just one vector with the same dimension of the data, right? So that's something to help you to generalize to other models. But now today we use a linear regression as a running example. Okay, so how we can find this data? Find this data given training example, height and weight of peoples. We have a lot of training example, right? Maybe we have 100 people with their height and weight. So I use N to denote the number of examples in the training data. So we have X, XI, Y is a specific example. So I give you this. Can you give me this? That's our goal. But how we can achieve this goal? Now that's why we need probability distribution. Let me make it in a probability. Transform it into probability objective. I will formalize it like this. I want to find the probability of this theta, this parameter, given this training example, right? One, I will find this optimal parameter when we maximize this probability. Make sense? If you can intuitively interpret this, I give you the training data. What's the most likely parameters? What's the most likely parameters? That equal to what's the biggest probability of this parameter, right? The two expressions are same. So now we translate into this form. But how we can find a theta maximize this probability? This is unsolvable. So we have to make it solvable. That's why we want to talk about something called likelihood. Anyone can tell me what's the likelihood? What's the relation between this probabilities and the likelihood? If you just do some research and pre-learning before, do you remember? This is normally called the posterior probability. Okay, let me give you what's the likelihood? Let me formalize the likelihood for you. Then I will ask you the same question. What's the relationship between this probability and the likelihood? The likelihood in this case is equal to xi, the probability of data given theta. Now I just put the position. I just convert the positions. Now it becomes the probability of data given the parameters. This is called likelihood. Anyone can tell me how I can relate these two? I need a formula. This one is equal to this one, and maybe do some operation. I'm not sure. Maybe multiply, maybe plus, maybe division. Which formula I can use to transform this to this? One is a property of prime given one. Yeah, you are correct. So they are like inverse of, no, it's not inverse of. This is very, actually, I would say the most important theorem in the statistic, but in the half the world of the statistics. It's called Bayes theorem. This is equal, what Bayes theorem tells us? Bayes theorem tells this: probability of A given B equal to probability of AB divided by probability of B. What's the probability of AB? Probability of AB equal to the probability of B given A times probability of A. This is Bayes' theorem. Let me erase this one. Directly get this. So this is Bayes' theorem. Let me apply this Bayes theorem onto this. Now this is A, right? This is B. Now I have B, I have A. I have multiplied by A. What's the A? A is theta. So P theta. Then I have divided by B. What's B? B is probability of data. Oh, good. Yeah, no problem. So let's have a look. Bayes' theorem is applied to the this our machine learning problem. Okay, so now we don't need to solve this. We solve this. We want to find the theta, maximize this. Let's look at this equation. We can eliminate this because it doesn't relate to the theta, right? We want to find the maximize this one for finding theta. So there is no theta here. So it's like a constant. It doesn't matter for the constant here. Then this is our goal. So for maximum likelihood estimation, we only care about the likelihood. We don't care about this. We don't care about this. This is called prior distribution. But for this one is normally you cannot find the distribution of the theta. Actually, we can assume the distribution of theta is uniform. But in anyways, in normal distribution, we don't care about this. But if you in the next week, I will teach you about the regularization. Then we will do something on theta. That's actually the how we can consider this term. But today we don't consider this. Today we talk about maximum likelihood. So we only need to consider this. Okay, let's solve this. But this is also, we can directly solve this. Because what we have, let's look at what we have. What we have is we have a model. We have in supervised learning case, we have model like this. We have model like, okay, given theta, given model, and give the output of the model. Please give me the input. This is what we have, right? So look at this likelihood again. What's the difference between this and this? The only difference is, okay, now I have X on the left side rather than right side. Do a little bit simplification. I want to move this X on the right side. You can think about, okay, X is a context, X is known, so its probability doesn't matter. Yeah. So then you can further simplify it into this max theta. Okay, now we have this one. Now what we should do? We know this, right? If I give you a model, you can randomly initialize your model, your beta 0 and beta 1. You can see beta 0, 2, beta 1, 3 never met. Then you will have training data. Then you know what's xi. Then you give your model will output some prediction of y. So, but you still don't know the probability. Actually, it depends. In the classification model, I will introduce next week. You will see we can directly get this, the probability. The model will output this probability for us. So, but in linear regression, what it will output? Linear regression will output y. What's the value of y? So how we can make this y to probability of y? This is the next question. Let me reformulate this question because we already solved from the beginning. Now the question become maximize. So now I want to make the theta to beta 0 and beta 1 because this one I still want you to remember this one because this one is used for all the supervised learning model. Okay, actually you can think about the previous one. Before I move this x to the right, I have something like this, right? If you remember x, y, this is the original likelihood, right? Actually, this one is for all the machine learning model, for supervised and supervised model, right? Because you see x, y, given theta, what's the x and what's y? In the supervised, unsupervised learning models, we don't given x, we don't given any known features to the models. So what we have is we have an unsupervised learning model like k-means, and then we will say, okay, what's the data? So that's actually for can be applied for the unsupervised learning model. Actually, I didn't introduce unsupervised learning model based on likelihoods. There exists unsupervised learning algorithm based on likelihood. I remember it's called EM. That's called the expectation maximization. Okay, this is likelihood algorithm for likelihood relevant algorithm for unsupervised learning model, but it's not topic for today. Also, this can be used for all the supervised learning model.